4 bar magnets by Jackson Greencorn. Let's get into it. So for a quick introduction, the purpose of this lab is to measure the dependence of distance of a bar magnet both on and off axis using calculations utilizing the Biot-Savart law. And with my results, I found that N equals negative 2.56 and that mu is equal to 1.7485 ampere meters squared. So for our fundamental principles, we have the natural log of the magnitude of B vector sub x equals natural log of K plus L in ln of R. And then we have the magnitude of B vector of the bar magnet equals KR to the N. You'll notice that the top and bottoms are very similar in the idea that it's only a natural log algebraic manipulation using natural log rules. And the rightmost equation is our traditional Biot-Savart law, mu naught over 4 pi times 1 over r magnitude of r cubed, multiplied by 3 times mu vector dot r hat times r hat minus mu vector. So for our procedure, here's a picture of my friends and I completing this. We put the bar magnet on either side of the ruler, place the magnetometer as close to the zero for correct orientation, and then slide the phone back and forth the stick either perpendicular or parallel to the axis and record data as distance varies. Step 1, you'll see in the picture up here, we have an east and west axis orientation. The phone with the red X on it is orienting the magnetometer as close to zero as possible. And then the picture in the middle with the blue arrows actually indicates us sliding up and down perpendicularly. Whereas if we oriented the phone 90 degrees clockwise, it would have been the parallel direction. Here are my results and my tables with one of my first results. From here, you can kind of see it. I should have moved this equation around. It says y equals negative 2.5608x minus 14.867. That negative 2.56 is our N value. Yes, that is our N value. So then for our calculation of our mu, we have the equation magnitude of B vector equals KRN. Well, then we have N equaling negative 2.56. Now we know that natural log of K is equal to negative 14.38, right? Because, again, we get this from here. When everything else is 0, K is equal to 14.8. So then we raise that to the E power, find that K is equal to 3.94 times 10 to the negative 7th. So then we use this to plug in for our B perpendicular. We find that our mu naught over 4 pi times 2 over mu over r squared equals k over r squared. Therefore, 3.94 times 10 to the negative 7th equals this expression, and therefore mu is equal to 1.74 ampere meters squared. Here's my computational model in GlowScript. This was given to us by the starter code, in which you just put in all of your described values from the experiment. We have all 6, both of the observation axes, and all 4 of the observation perpendicular distances. Then we have over here to the top right, we have our perpendicular radii, and you have to actually make 4 of these instead of just the 2 that I have shown. But here are here's the 2 axes, and then at the bottom right we have the product of this. We have our 45-degree angles, we have our electric field at 45 degrees, and then we have our printing values, and here they are. We have that this magnetic field looks like a produced dipole, going out at the right, back in when you go up or down, and then back to the right as you close into the center. We have our distance equaling 1.99404, which is perfect. B at 45 degrees equaling that times square root of 2, which is perfect. So our possible errors is user error, magnetic fields in the surrounding area, because we were surrounded by other technologies that have circuitry, which we know carry magnetic fields. It could have been a faulty device error, or the assumption that the bar magnet acts as a magnetic field. This is a idealization, not a perfect instance. If we hadn't oriented your experiment to compensate for the magnetic field north, it means that our directions would have changed. Magnitudes would not have. But what if we were to stick 2 identical magnets together? Well, that means that the perpendicular magnetic fields wouldn't really change, but the parallel ones would, due to like poles strengthening each other. This has been Lab 4 by Jackson Greencorn. Thank you very much